Welcome to today's chemistry lecture. In this lecture, we are going to study the arrangement of ions in salt, melting points of ionic compounds, and conduction of electricity by ionic compounds. We will see every concept step by step and point to point with solutions. So our first concept is arrangement of ions in salt. When acid neutralized base or alkali salt and water are formed. For example, when an acid reacts with base, they neutralize each other to produce salt and water. Sodium hydroxide reacts with hydrochloric acid to form sodium chloride and water. This reaction called the neutralization reaction, where an acid and base react with each other to form salt and water. The ionic bond. A salt is a chemical combination of positive ions, cations, and negative ions, anions. These oppositely charged ions are held together by strong electrostatic force of attraction. The strength of this attraction depends upon two main factors. First, magnitude of the charges, and the second, distance between the ions. Let's see the magnitude of the charges. Higher will be charger means stronger attraction, and distance between the ions at that smaller the distance means smaller the ions mean stronger the attraction. To understand this concept clearly, let's see the figure 18.1 crystal lattice of sodium chloride. Under ordinary condition of temperature and pressure, ionic compounds exist as crystalline solids. Instead of forming isolated molecules, these ions arrange themselves in a highly regular, repeating three-dimensional pattern called a crystal lattice. Let's see the structure of sodium chloride. Sodium chloride forms a specific geometric shape known as face-centered cube. Ionic coordination. Each sodium ion is surrounded by 6 chloride ions, and each chloride ion is simultaneously surrounded by 6 sodium ions. Ion placement. The larger the chloride ions are located at the corner and the center of each face of cube. The smaller the sodium ion occupies a space along the edges of the cube. Here is something information which says that common salt was a valuable commodity in the past. It was even used as currency. Means in ancient time people used the stone of salt for currency. Now let's see the second concept, which is melting points of ionic compounds. Because the ions inside a crystal lattice are bounded by incredibly strong electrostatic forces, a significant amount of thermal energy is required to break these bonds apart. They have high melting points. This intense structural strength explains why ionic compounds generally have very high melting points. The melting process. When an ionic solid melts, the heat energy overcomes the rigid attractive forces, allowing the tightly locked ions to break free from their fixed position and move around fluidly. Factors affecting the melting points are higher ionic charge or smaller ionic size lead to much stronger electrostatic attractions. Stronger attraction means more energy is needed to break the lattice, resulting in the higher melting points. Now move to the third point, which is conduction of electricity by ionic compounds. An electric current requires the movement of charged particles like ion or electron. The ability of ionic compounds to conduct electricity depends entirely on their physical state. Solid state mean non-conductors. In a solid crystal lattice, the ions are tightly locked into fixed position by strong attractive forces because these ions cannot move freely. Solid ionic compounds do not conduct electricity. Molten or dissolved state conductors. When heated to a molten liquid state or are dissolved in water, the strong forces holding the lattice together break down. The ions become free to move independently toward oppositely charged electrodes, therefore, they readily conduct electricity. Strong electrolytes. Ionic compounds are classified as strong electrolytes because they dissolve, split apart completely into mobile ions when dissolved in water. Let's solve the quick check problems. First question is how the ions present in sodium chloride arrange themselves to form a crystal lattice. Let's see the answer. The ions in sodium chloride arrange themselves in a regular repeating three-dimensional pattern known as face-centered cubic crystal lattice. Each positive sodium ion is tightly surrounded by six negative chloride ions and vice versa. The larger chloride ion occupy the corner and the corner center of each face of the cube, while the smaller sodium ions fill the edges of the cube to maximize the stability of that lattice. Now move to the second question. Do you expect melting point of potassium chloride to be higher or lower than sodium chloride? Let's see the answer. We should expect that melting point of potassium chloride to be lower than the sodium chloride. Reason? Both compounds have the same ionic charges +1 and -1. According to periodic table, potassium is located below the sodium, meaning a potassium ion has more electron shells and a larger ionic radius than a sodium. Because the potassium ion is larger, the distance between the nuclei and the potassium chloride lattice is greater. This results in a weaker electrostatic force of attraction compared to sodium chloride. Since the bonds are weaker, less thermal energy is required to break the lattice, resulting in a lower melting point of potassium chloride.